Hello, this is our CVPR 2026 paper, Detecting Unknown Objects via Energy-Based Separation for Open-World Object Detection. To deliver our work more clearly to our international audience, this presentation was produced using an AI text-to-speech model. Our story starts with open-world object detection. In this setting, the detector must do two things at the same time. It detects the known objects it was trained on, and it marks objects that were not in the training data as unknown. Then, over several tasks, it learns new classes, without forgetting the old ones. On the right you can see our two goals. First, separating the known space from the unknown space. Second, separating previous task classes from current task classes. When we achieve these two goals, the features become well separated, as shown in the PCA plot on the left. In the baseline on top, known, unknown, and background features are mixed together. In our method on the bottom, they are clearly separated. Let's look at a real example. Previous methods decide unknowns using only the known class predictions, so they often make mistakes. Here, a giraffe, which is an unknown object, is wrongly detected as horse, a known class. A cow, which is a known object, is wrongly detected as unknown, and one unknown object is completely missed. In short, existing methods miss unknown objects, confuse them with the background or with known objects, and also suffer from interference between old and new classes during incremental learning. These are the problems we solve. This is our method DEOS. The important part is what each loss does. A proposal, which is a candidate object region, comes into the detector. For the first part, EUS, we build two spaces using an ETF, an equiangular tight frame. This is a fixed basis that is not learned. One space is the known space, and the other is the unknown space. For each proposal, we compute an energy score in each space. The score means how close the proposal is to that space. As shown on the right, known proposals go to the known space, unknown proposals go to the unknown space, and background stays at the boundary. At inference, we use this to calibrate the unknown score. For the second part, EKD at the bottom, we use the same idea on the task heads. We split the classifier into a previous task head and a current task head. Each proposal is trained to have a high score only on its own head. Here are the actual losses. For EUS, we compute the known score in green and the unknown score in red, and the EUS loss uses these margin to push them apart. For EKD, the loss makes the previous task proposals and the current task proposals each prefer their own corresponding task head. The total loss simply adds these two to the standard detection losses. These are the main results on the Open World Object Detection benchmark. Look at the unknown recall column in gray. Our method reaches 65, 66, and 69 across the tasks, which is clearly higher than all previous methods. At the same time, our known mean precision stays stable as the number of tasks grows. As a result, we get the best harmonic score on every task. From task 3 on, we also reach the best known average precision. This shows our method handles both unknown detection and forgetting well. Finally, we check that each part works as designed. On the left, proposals matched to known classes have a higher known score, in green, and proposals matched to unknown classes have a higher unknown score in red. So EUS aligns each proposal with its own space. On the right, the heat maps show the task head energy. With EKD, the diagonal goes up and the off-diagonal drops, which means each proposal is routed to its correct head. And the whole method is a lightweight and plug-in, with only 6% more training and 2% more inference time. Please see our paper and poster for more details. Thank you for watching.